Hello and welcome. So today we're going to talk about valence electrons. Valence electrons, in my view, are the most important electrons when talking about chemistry. They are on the outside of the atom, which means they're accessible for doing chemistry. That is to say, making bonds, breaking bonds. They're involved in bonds, connecting atoms together. And as we'll see in a different time, we'll talk about how electrons, they can either be shared or you can transfer electrons between atoms in the process of forming ions. But all those processes of making or breaking bonds, of doing chemistry, has to deal with the electrons that are on the outside. And those are called the valence electrons. All right. Versus a core electron, these are electrons so close to the nucleus, they are so attracted to the nucleus that they're basically not available for too much of chemistry. So our focus from here on out is going to be valence electrons. All right, so we have to figure out where they are. Where do we find these valence electrons? All right, so I got some goals for today. We already talked about what a valence electron is. We already talked about where they can be found. We'll have a little bit more to say on that. And then we're going to talk about something called an orbital shape. All right, I'll just leave that as a question mark for now. And then we're going to close with using the periodic table to predict orbital shape. All right, let's go. All right, so first, this is a very important idea, which is where do we find electrons on an atom? Said another way, would an electron be as close as possible to the nucleus, or would electron be better off far away? Well, electrons don't really get to choose. Maybe that's the wrong way of putting it. We're just trying to think of what nature does automatically. So we have a positively charged nucleus with the protons inside, and then we have electrons negatively charged. So to maximize attraction, electrons will go towards the nucleus. They're going to be as close to the nucleus as physically possible. All right. So a question might become, is the electron going to be right on the nucleus? Is there maybe some space? So we'll get there, but the basic idea here is electrons go as close to the nucleus as they possibly can. That's just what nature does. All right. And we have a name for this. This is called the ground state. Just like you don't see me floating around in this room, I am sitting, I am on the ground, okay? So just like objects go to the ground. Ooh, that was too loud. Objects go to the ground. So do electrons. They go to the ground, or it's the nucleus, all right? If you were to push an electron away from the nucleus, that can be done through putting energy into an electron. That can be done through various things like heating up your atoms, so just heat, electrical current. You can even hit the electron with photons, push it away. After you put in that energy, that electron is going to find its way right back to be as close to the nucleus as possible. But when that electron is momentarily pushed away, we call that an excited state. All right. Most of our conversations here are going to revolve around electrons being in the ground state. In other words, we're going to be talking about ground state atoms. Okay. Now, we're trying to form a physical picture of how electrons are arranged on an atom. Okay, in an earlier video, I talked about the Bohr model. So in the Bohr model, you imagine electrons moving around as like planets go around the sun, and you would maybe call them orbits. So if electrons had to travel in orbits, hopefully it stands to logic that it would be in the closest orbit possible so that it is as attracted to the nucleus as it can be, all right? And that would be our so-called default position, all right? That's where the electron is happiest, most stable, good stuff. Lowest energy, if you want to use physics terms, all right? And like I drew in the the previous slide, an electron further away, we had an outer orbit, it would find its way to going back to the closest orbit possible. Again, that's ground state versus excited state. All right, but are orbits really the way electrons exist? And the answer is no. All right, this is where chemistry can feel a little bit strange and weird, but we're going to try to simplify it. So electrons, all right, let me put it this way visually. All right, if you were to draw a nucleus and then you were to draw where an electron could be at any point in time, if I were to let this run after like 100, 200 different points in time, or maybe a million, just a lot, hopefully you get the idea, you would get a plot something like this, all right? And you can see that the number of times the electron is close to the nucleus or even inside a nucleus is much higher compared to being away, all right? This is like a probability plot, all right? The way we interpret how electrons behave, or the way we have equations that describe electron behavior, this probabilistic way of describing the electron seems to be one of the best ways of describing where we can find the electron, all right? And electrons move fast, all right? Not quite the speed of light, but you're almost approaching it, you know? So we're going at fast speeds, and so you plot this many times, 100 times, 1,000 times, a million times, billions of times, you'll eventually just kind of see that after so many different spots, we can just draw something more practical. We can draw a sphere, okay? And in this sphere, it shows 90% of the time the electron can be found in this space here, all right? So you study like Schrodinger's equation and probability and stuff like that. For a 101 course, that's certainly not required. But we're going to study those things. The electron, technically speaking, this is a little weird, but it has a really slight possibility of being like really away from the nucleus. You can go out to a distance of infinity, and you know there's like, maybe if I were to draw this as a graph. Okay, if I were to draw this as a graph and I have like distance going this way, R is for radius. If you're like to start at the center of the nucleus, all right? Oh, I'm covering that. All right, so here's my graph, R distance. And then we had like a probability of finding the electron. You can see if I use this part being in a nucleus as the highest level of probability, and then we're going further away, you can see that we're at high probability. Oh, it's going lower, 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 lower. It gets really low. And then you get the fancy math word is asymptote. Someone's going to look up that word. Asymptote. All right, I don't really say the P too much, but it's like about to touch a line, but it like never does, all right? And so you can see by the time you're quite far from the nucleus, basically, practically speaking, you have zero probability, all right? To get a reasonable shape, though, some people, they'll just choose to draw their shapes at like 50%. I kind of like 90%. I shuffle in between sometimes. That percentage actually isn't overly important, but we can get these more practical shapes. You can see how that ends up being just a simple sphere, and we can call that the electron cloud. A lot of people like to talk about how electrons are moving so fast. Is basically the entire blur of the electron motion. That's just your cloud, all right? And you can basically think of that as the electron itself. That's the way I basically like to think of it, all right? And so, yeah, that's how we're going to draw these orbital shapes, okay? So rather than an electron going in orbits, we now have these orbitals, which come from solutions of what's called the Schrodinger's equation. Again, I would never put this on a 101 exam. But it's all based on the mathematics that describe the data best of where we find electrons in an atom. So it's all rooted in the math describing the physics of the atom, all right? So you can look up Schrodinger's equation, but that's where all of this is coming from. For one-on-one purposes, I want to keep this as straightforward as possible. So just for those interested, I wrote that there, but we'll just move on. All right, so this is where I think it's kind of cool and weird. the sphere is kind of an intuitive shape, all right? And for when you're starting out describing electrons, let's say we're talking about the most simple atom possible, a hydrogen atom, you get these sorts of shapes, all right? And that first electron, the only electron for a neutral hydrogen atom, it'll exist in this kind of spherical space. But as we'll see later on in the next video, we're going to have these other shapes that are possible, all right? And so we can have spherical shapes for the electron orbitals. I never describe where the word orbital comes from. Orbital is just, we call it orbital because we know it's truly not orbits. So we just said, let's just use a similar word. So that's where orbital came about. But we can have these spherical orbitals. We can have these dumbbell shape or figure 8 shapes. And you can just kind of see in terms of the number of like lobes, we go from one area of space, that's an oxymoron, whatever. One space to like 2 spaces, and then we go to 4, and then we go to 8. That one's hard to draw, the double-clover sphere, dumbbell, double dumbbell or a clover, and then we have a double clover, or you can say a double dumbbell, where we have 8 possible regions. And these shapes are really interesting. Like for the spherical shapes, you can have the electron exist like literally in the nucleus, okay? Whereas for a dumbbell shape, you can, but basically just at one exact point. And anything outside of the shape, you're not going to have the electron exist in those spaces. That kind of has to deal with the wave nature of the of electrons, all right? This wave nature of matter that becomes apparent at really small distances, okay? And so, like, if I were to draw a sine wave, okay, sine wave, okay, like a sine x function, all right, you get something like that, all right? You know, you have area here, you have area here, but right here you have no area, so we call that a node. We have a node right there. But that's a 2D wave. These wave functions for describing electrons, they're in 3 dimensions, all right? So if I had blown up some balloons, I should have done that, but if I had blown up some balloons and I tied 2 of them like together, it'd be kind of like that. If I took 2 of these balloons and tied them together, I'd get that, and so on, so forth. All right. Now, these orbital shapes are not terribly important in Chem 101, other than to know that they exist. And some Chem 101 courses, maybe they'll stop right there. Some might stop right there. Now, I used to be a uranium chemist, and so I had to deal with F electrons a lot. So I like to draw those. I wouldn't put that on the test. That's hard enough for me to draw. All right. But practically speaking, knowing the orbital shape can begin to give us, and here's my final slide for today, some sense of organization of the periodic table. All right. So I drew 4 different regions here, and I can take my real periodic table. Okay. We have different block names here. So this is called the S block. This is called the P block. This is called the D block. And then this last part that we had to move out so it could fit into a single sheet of paper. All right, let me get that camera moved. There we go. This is the F block, all right? And as I'll remind you in the next video, it's good to think in that order. S, P, D, F. S, P, D, F, the special PDF file is my little nickname for it, all right? If you're wondering why that order, well, the numbers tell us so. 1 starts in the S block, where with hydrogen. Helium, as we'll talk about a little bit more later, but it actually belongs, when we're talking about electron arrangements, I'd say helium might be better off right here because it has also another S electron. If you know something about noble gases, maybe that's why helium's here. And that is why I like to call helium a dual citizenship element. All right, it likes to hang out here because it's a noble gas, but this is where it came from. All right, but yeah, 1, 2, and then 3, 4, and then 5. That's our first p block element. So we want S, P, and then potassium 19, calcium 20, scandium 21. So the D block appears third. And then cesium, barium, 55, 56, and then 57, lanthanum, cerium, praseodymium, so on and so forth. Here is our F block appearing last, all right? And yeah, that's the power of the periodic table. Another one of its powers is based off of where an element is on the periodic table, whether it's the S, P, D, or F block. You'll have an idea of what those electrons, those orbital shapes look like for the valence electrons, the electrons on the outside. All right, the next video, we will put this together by showing the address for these electrons. You're gonna write out an address, a map, whatever you wanna call it, for every electron in an atom. And after you write that all out, you will know which electrons are the valence electrons, which electrons are the core electrons, valence and core. We're going to do that through writing things called orbital diagrams and electron configurations. But I think this is a good stopping point. All right, hope this helps, and let me know if you got any questions. Take care.